All right, so there's one more part of the bird's eye view. I will get through part of this time, and then I will probably finish it next time. So the final part, remember the first part was hardware, second part is software. The third part of this, which will be a big part of the class, is the sensation and perception part. So this is the biological, the neuroscience, the perceptual psychology part, sensation and perception. So how do the senses work and how are they interpreted by the brain? Sensation and perception. So there are a lot of relevant VR questions here. How do we perceive depth? Right? How do we know how far away something is? I think most engineering students would answer by stereo, right? Stereo vision, right? You've done computer vision projects before perhaps where you reconstruct depth from stereo images in a camera. It turns out that a very, very large overwhelming amount of depth information comes from monocular vision, just from a single eye, from the brain's expectation of where everything falls together in the physical world. So you get a lot of depth information from that. So they're called monocular depth cues. That's something I want to cover. So in engineering people tend to overemphasize stereo when the truth is monocular depth cues provide most of what you need, and for many applications it may provide everything that you need, in which case it simplifies your engineering design considerably. What causes nausea or fatigue? What are the root causes of these? It has to do with sensation and perception. The information coming from these sensors, you've engineered alternate stimuli now to present to the senses, which confuses your brain. Sometimes your brain doesn't mind, sometimes your brain may respond by causing you to want to vomit, right? So what's going on there, right? How do we understand these things and try to avoid these problems? How do we perceive the source of an audio signal? Where is the sound coming from, right? I've noticed on the campus here there are these incredibly loud birds called the Asian coal, right? Not sure what your local names are for them, but very loud. I notice when I step outside I can identify which tree they're in very, very closely, which is quite interesting when you think about it. We don't have a full imaging system for our ears. How are we able to do that, to localize the audio source, to pinpoint where something's coming from? How much resolution is enough on a display, right? How do you answer a question like that? Well, you need to take the human body part, the human vision, or the organism's vision part into account. And this whole idea of presence I gave you a little bit of an idea of, but we can get more into that as well. The thing that's very confusing is that the processes that are going on for us all the time in our daily lives, we're using perception constantly. Our brains are doing a lot of work to build a coherent view of the world around us, and you know what, it's effortless, right? It appears effortless to us. It's not something you spend a lot of time on. You understand where you're going and what you're doing, but if you really stop and think about it carefully, you're doing very, very complex tasks, ones that are very, very hard. You have around 10 billion neurons in your brain doing a lot of work. A huge fraction of those are devoted to vision interpretation, and you know, the best computers we have, the best machine learning algorithms, okay, they're getting better these days, but they still can't compete with the human brain, and it's quite impressive. And all this work seems to be happening effortlessly for us, right? So we're not even trained to be aware of it. If you do virtual reality, you need to be trained to be aware of these things because you're interfering with their operation. So if you want to be a good VR engineer, you have to understand some of the reverse engineering of the human brain and the human vision system and the other senses in order to be a good engineer of virtual reality systems. So that's why these things come together and why we're motivated to study these. I've already talked about different senses. I want to go into a little bit of classification of senses. So I just want to talk about, for each one of our senses, what is the sense called? What is the fundamental stimulus? What are the receptors? What is the familiar sensory structure or sense organ? Or organ? And I might not hurt to think about some kind of engineering equivalent. Again, this is just a bird's eye view, so I just want to quickly go through these. So for vision, that's the name of the sense, vision, human vision, let's say. What's the stimulus? Electromagnetic energy. So just think about it, electromagnetic energy, or photons if you like, right? So electromagnetic energy in what's called the visible spectrum. Why do we call it that? Because we consider ourselves to be important. We've selected that part of the spectrum because that's what our eyes respond to, right? Call the rest infrared, ultraviolet outside of that. All right, but it's all electromagnetic energy. On your retina of your eyes, you have photoreceptors. Just like you have pixels on a display, those are the output pixels. The photoreceptors are like input pixels. So these are the parts where you sense. The sensory structure, well, it's the human eye. The engineering equivalent, I guess, would be a camera, right? And the way we design cameras is very similar to the way our eyes are designed, except all these extra movements and things that our eyes do is very complex and interesting. Let's go for another sense. So that was one of them, vision. The next one is hearing. So if we go to hearing, sense is called hearing. What's the stimulus? Yeah, so air pressure vibrations, or air pressure waves, let's say, right? So it can be considered as a kind of mechanical vibration. Good that you use the word mechanical because the receptors are called mechanoreceptors, right? So we can get into a little bit of the details when I cover audio, although I'm mainly going to be covering vision. Of course, the sensory structure is the ear, and I guess the engineering equivalent would be a microphone, perhaps, right? We put microphones, which are very close in design to speakers. Let's see, if we go through touch, right, so the sense of touch, in this case the stimulus is tissue deformation, right? So the surface of your body is deforming in some kind of way. We have mechanoreceptors for that. We also have thermoreceptors. So part of touch could also be a change in temperature, right? You feel that something's burning hot or a cold piece of ice on your skin, right? So it can also be thermal. So there's thermoreceptors and mechanoreceptors. Sensory structure, skin all over, muscular structures and all throughout your skin you have the sensory structure. So that one's the most distributed across your body, right? So we could break that into further and further finer categories if you like. In the engineering world, we have pressure sensors and force sensors and thermometers, right? So we make all kinds of things. The physics is the same either way, so there's usually an engineering equivalent for the things in our bodies. One extremely important one for us, and this has a lot to do with simulator sickness, is our sense of balance. It turns out that we have inertial measurement units inside of our ears, and it's not part of the hearing system, it's part of our balance system. So the sensory structure organ is called the vestibular organs, which are mainly located in your inner ears. There's a pair of them, and the stimulus is accelerations. Could be due to gravity, could be due to linear motion. So that's the stimulus that we get, or accelerations, and there are again mechanoreceptors for receiving that information. So it's one of the most mysterious organs. We rely on it every day, but most of you probably haven't thought too much about how it works or what exactly it's trying to accomplish. Other than from its name, it's obviously helping us to balance. And finally, I'll put these both together, taste or smell. So in this case, the sense is taste or smell. The stimulus is chemical composition, right? So we have some chemical composition, and it turns out in this case we have chemoreceptors, right? So some kind of chemical receptors. If there's a change in the pH, for example, in acidity, you may be able to measure that and send signals to your brain. Sensory structure, well, these would be in our mouths and nose, right? In the surface of our tongues, the inside of your nose. So you have places where you have these chemoreceptors that can measure these chemical information, chemically based information as it propagates through the environment. So among all of these senses, the one I'm going to cover the most in this course is vision. Number 2 is the hearing part, and I'm going to leave off the rest, right? But they all can be considered very important. You can easily spend an entire course on the touch part, many fascinating issues there. Balance is going to be important though too. I better put that in here. We're going to cover some of that because that becomes extremely important for making comfortable experiences. And let me mention one small thing here and then I'll finish up for today. So which is as these senses come together, if you're taking control of one of the senses by providing alternative stimulation and then you've neglected the other sense, your brain may not become happy about integrating those two sensors now because it's going to start detecting mismatches. And those mismatches might happen at a subconscious level and you may become uncomfortable or sick from that. And these are the kind of difficulties that happen. So the most important for us is vision plus balance. When you mix those two together, balance or vestibular, you have a problem. One of them is called vection. Again, this is just a high level view. What happens in this case is this is the illusion of self motion. Have you ever been sitting on a train and the train is stationary and out the window another train starts moving and you get the sensation that you're going backwards but you're not moving? That's an example of vection. So your eyes have convinced you that you're moving and accelerating, but your vestibular organ knows that you're not, and it's disturbing, right? It's really unusual. So in virtual reality you're doing that over and over again every time you grab onto the controller and move your character. You're convincing your brain that you're moving, but your vestibular organ, your balance organ, knows that you're not. So that's a problem. It's called vection. What do we do about it? Not completely sure. I have some suggestions, but a lot of people are working on how to overcome this. Another interesting thing I mentioned, it's called the vestibulo, mentioned it once already, ocular reflex. Or VOR. This affects our perception of stationarity. So if I put something in front of my face like this piece of chalk and I go back and forth like this, my eyes are counter rotating with respect to the rotation of my head. It's a perfect one-to-one correspondence. It's a very tight feedback loop that takes less than 10 milliseconds and bypasses my higher level brain functions. It's a very tight control system that's been evolved to do this, and it affects my perception of stationarity. It's very hard to not do it. You can try to not do it and just have the chalk look like it's going back and forth instead. Very, very difficult. You can put your finger in front. Go ahead and try this. Put your finger in front and go like this. It won't hurt, so you know, right? So you're doing this all the time. This affects your perception of stationarity. You have to get that exactly right in virtual reality. If you have optical distortions or you have latency, other things, your brain may learn to compensate for that. And then when you take the headset off, the real world will be messed up for you. Those of you wearing spectacles, you'll notice that you may notice that when you take them off, the world might look like it kind of swims back and forth. Your brain actually has learned a different gain constant for your spectacles or glasses. When you wear those, due to the magnification of your lenses, the counter rotation rate is different than the rotation rate. But your brain learns that. It's no problem. So if you have a bad virtual reality headset, your brain might learn to compensate for its flaws, but it's not going to tell you that it's doing that. You'll just think it looks right because your brain's adapting to it, and then after 20 minutes you might have a headache or feel sick or something, you know, and your brain's trying to compensate for these things, pushing the limits. It's better to engineer it correctly and make it comfortable, but these things tend to be invisible to people. So this is a very important intersection or combination between two different senses. Is there any which equivalent?
Engineering equivalent.
Yeah, that's a very good. So you could provide vestibular stimulation. Maybe you provide some kind of vibration that distracts the sense enough. You could do electrical stimulation of the vestibular organ, but it tends to be painful. I don't think there's an easy source, but that's a very natural thing. Of course, just make all the senses become together in harmony, and that would be a solution, right? It's just very difficult to engineer that. Low frequency vibrations and rumbles might help. There's been some research on that, but it's not, I don't think it's completely conclusive. So a very good question. All right. I have a little bit more left on this. I don't know if I could either take 10 minutes or wait till tomorrow. I don't know what's best. Should I finish it? All right, I'll just finish it up so that we hit it in one shot. So a few more things on the bird's eye view, and then we get a clean shot into the rest. if you read the first chapter of the book by Mather on sensation and perception, you'll get all of this in much more detail, and I think it'll be very helpful for your perspective as you go through this class. So I just want to introduce a few small concepts here in the remaining 5 to 10 minutes. The subject of psychophysics. All right, so this is the scientific study of connecting physical stimuli to perceptual phenomena. Perceptual phenomena. So your brain reacts and comes up with some conclusion. For example, what does it take? What do I have to present to your eyes so that you declare that something is red instead of blue or instead of orange? Right? What does it take for you to declare that something is bright or dark or loud or sour? What does it take for you to declare that something is sour if it's taste, right? So these are really interesting questions, right? So one of these is clearly a reaction of the human, but it starts with physics. That's why it has physics in it, it has psycho in it. You put these two together and you design scientific studies for that. So there's usually a kind of plot in a lot of these works that looks something like this. You'll have a probability of detection, and then you may have, let's say, a stimulus parameter here. And the plots could look, you know, varied depending on the experiment, but perhaps it looks something like this. Probability should go from, say, 0 to 1, but maybe for some particular experiment there's like some crossover point where everything should match perfectly here. So that's some kind of parameter. For example, maybe you're changing acidity in some kind of taste experiment so that at some point it becomes it gives you a sour taste, let's say, right? So you have a whole bunch of subjects and you get them to start trying, you give them these chemical taste tests as you vary your parameter. So down here nobody would say that it's sour. Over here when you turn the parameter to some extreme, everybody will say it's sour. And then there's some kind of in-between region where, you know, around in the in-between region some people will say it's sour and some will not, right? So that's the kind of experiments people do in psychophysics. They vary, they turn knobs and they try it out on people and they see what happens. They may also be measuring response times to stimuli. Sometimes you need 3 or 4 subjects and that's enough. Sometimes you may need 100 subjects or more. Sometimes you may have to consider demographics of your subjects. Could be age, gender, various things might matter. Some other kinds of studies it might not matter at all. It may have to do with just a common wiring that's in all of our bodies and it doesn't really matter. Therefore you need 3 or 4 subjects and you're done. So it just depends on a lot of things like this, and it's a very scientific, rigorously defined subject, and there's all kinds of interesting results from that. One of the most interesting general patterns that seems to come up over and over again is called Stevens' power law. So let me go into that. Let's see. Stevens' power law. This is from around, let's see, I think 1961. Let's say m is the magnitude of the stimulus and p is the perceived magnitude. Perceived magnitude. This is a pattern that will show up over and over again, and it definitely shows up throughout virtual reality. So there's a kind of mapping, looks like this. P is equal to some constant c m magnitude to some power x called the exponent. So c is a constant, depends on the units, depends on some kind of curve fitting. So people have done many, many experiments with human subjects in many different settings, and they end up with plots like, if I put m on one axis and p on the other. So I increase the magnitude of the stimulus and then I measure the perceived magnitude by the person based on what they tell us. There are some cases where it'll go like this, in which case the exponent is greater than 1. There are some cases where it appears to be perfectly linear, and there are some cases where it goes the other way. It's very easy to find examples of this. If you look up Stevens power law on the internet, you'll find lots of examples. So it goes off in this direction in the case of x less than 1. And so as an example, if you take a look at loudness, you ask somebody, is this twice as loud or not, right? You can keep doing experiments like this. Give them a bunch of signals at, let's say, a single pure tone at 3,000 hertz, and then you start varying its amplitude and you try to measure their perception of how much the amplitude is going up, right? If you do this, the exponent will be 0.67, about 0.67. So it looks like this. So it starts getting louder and louder, but it kind of tends to saturate. You know, it doesn't really, it isn't perceived as being that much louder. Interesting, right? If you ask someone to estimate how long a line appears to be on a screen, it ends up being linear. They're pretty good at it. At estimate, as long as there's no other strange interference or optical illusions, they end up estimating it to be twice as much. So that's interesting if it's really twice longer. If you electrically shock somebody, then it looks like this. A little bit more shock feels a lot more painful. So, so these things all depend. That's Stevens power law. Another thing that tends to happen over and over again, and this I mentioned already with the vestibulo-ocular reflex, is plasticity and adaptability. So over time you tend to adapt. So if there are flaws in your virtual reality system, you adapt. If something sounds really loud, after a long time listening to it, it won't sound so loud anymore, right? So all kinds of things happen through adaptation. So that's just another very, very powerful principle which I need to emphasize is adaptation. Okay, so one last thing I want to say is I want to present some optical illusions to you just to help emphasize to you how much processing is going on that you might be barely aware of. So you might have seen some illusions before. There are visual illusions, there are audio illusions as well. There are all kinds of interesting things that happen. I'm just showing visual illusions because that's the main emphasis of this class. So let me put some up here. Have you seen this one before? So it seems, how many legs are there? I don't know. So you can present things that look reasonably plausible as long as you don't stare too closely. This one's great. Which one of these line segments is longer? Right? Turns out they're the exact same length. Right? So the upper line segment here, the lower line segment here, same length. Doesn't look like it. I think it looks like the lower one is shorter, correct? We can play the game like this. Which one of these line segments is longer? Right? These are perfectly vertically aligned, but this monocular depth cues that I talked about, that gives you the sense that the upper bar here is far away, gives you a feeling that it must be longer, but it's not. It's the same length, right? So your brain is doing all this work for you, and people who work in vision science, like their job is to be a scientist and study all day long human vision. They love finding new examples like this that reveal something that's going on when you're doing the reverse engineering of our vision. This one's pretty good. So the gray square here labeled A and the gray squared labeled B are the exact same intensity. Doesn't it look like A is darker than B? They're exactly the same. You can look up, you can grab this image and look exactly at the pixels if you want. They're the exact same RGB values. They're exactly the same. It's just the shadow effect that's causing this gray square illusion. So as your brain tries to integrate the whole picture together, it's going to tell you that B must be lighter, but it's not. It's the exact same shade as the A. That one's crazy. Does it look like the wheels are rotating? Well, they're not. Do you see motion in that? So your eyes have very, very tiny motions called microsaccades, and they're always doing that to refresh your photoreceptors. This illusion appears to confuse that, and it gets especially bad when you get up closer to it. Maybe I can leave this at the end of the lecture and you can get up closer to it. Especially bad at the periphery. And finally I'll end with this. This is called the haunted swing. This was made over 100 years ago in a festival, and a bunch of people get into a swing and then the entire room around them is actually rotating, but they don't know that. So the people who designed this, they took the furniture and they nailed it to the floors, and then they actually spin the room so that people perceive it as they are moving here and sitting upside down, but they're actually not, right? They just perceive it as that. So this generates vection, and guess what? The people got very sick from this, right? So this is exactly the kind of thing that's going on. This looks like virtual reality to me in a lot of ways, right? They tricked them with exactly these kind of motions. You know, it gradually starts rocking back and forth, and then you're convinced that the swing is going completely around 360 degrees, but really you're motionless, right? So again, another kind of optical illusion. So that completes the overview. That's the bird's eye view. I covered the hardware part, the software part, and the sensation and perception part, and gave you motivation for this class. So the next lecture I'll get into the basics of geometric modeling and some of the transformations that we apply. These are the beginning steps of making alternate world generators. So you can look at chapter 6 of the graphics book by Shirley et al. If you want to get started on some of the basics of that, if you don't have that math background and things. Thanks.